All right, welcome to The Explainer. Today we are diving deep into the heart of network architecture, Layer 2 versus Layer 3 switching. Getting this right is absolutely critical if you want to build a network that's not just fast, but also resilient and ready to scale. So let's get into it.
So here's how we're going to tackle this. First, we're going to expose the fundamental weakness of a simple flat Layer 2 network. Then, we'll look at how VLANs try to fix that. But, and there's always a but, how they create a whole new problem. That will lead us straight to the Layer 3 switch, where we'll pop the hood and see the hardware that makes it so darn fast. And we'll wrap up with a straightforward guide on when you should use each one.
Okay, so first things first, before we can even talk about the solution, we really need to get our heads around the problem. We're going to start with a network built entirely with Layer 2 switches and uncover the one critical vulnerability that this design creates.
So, in a simple, flat Layer 2 network, like this one, everything is in one giant broadcast domain. What does that mean? Well, when one device sends out a broadcast frame, say an ARP request, to find another device, that frame gets blasted out to every single port on the switch. It's kind of like shouting in a library. Everyone hears it, whether they need to or not. Simple, yes, but also incredibly fragile.
And here's where that fragility can go catastrophically wrong. All it takes is one bad cable, one little loop, and you've created a feedback loop for those broadcasts. This kicks off what we call a broadcast storm, and it will chew up all your bandwidth, effectively grinding the entire network to a standstill. I mean, it doesn't take much. I've personally seen a small data center with just a few switches completely taken down by this exact problem.
Okay, so how do we fix this? How do we stop this from happening? Well, the first line of defense is segmentation. And that's where network engineers bring in virtual LANs, or VLANs, to logically chop up that single, huge broadcast domain into smaller, safer, more isolated chunks. You see, a VLAN lets you group devices logically by what they do, not by where they're plugged in. So, for instance, you can stick all the developer machines in one VLAN and all the marketing team's devices in another. They effectively become their own separate, tiny networks, their own broadcast domains, even if they're all connected to the very same physical switch. So how does this magic work? Well, it all comes down to something called VLAN tagging, using the 802.1q standard. When a frame comes into the switch sticks a little digital tag on it that says which VLAN it belongs to. Then, the switch is smart enough to only forward that frame to other ports that are members of that same VLAN. This is huge! It keeps broadcast traffic contained and adds a really important layer of security and performance.
Okay, but this awesome isolation, it actually creates a brand new headache. We've successfully built these nice, safe walls to contain broadcast storms, but now we've also built walls between our departments. So what happens when a developer actually needs to talk to a server on the marketing VLAN?
All right, let's run a little experiment here to see exactly what I mean. We've got a standard Layer 2 switch. Node 2 and Node 3 are chilling out in VLAN 2. And over here, Node 4 is in VLAN 3. The mission is simple. Get traffic from VLAN 2 over to VLAN 3. And the result? Zero. Nada. Not a single bit gets through. The traffic just hits a brick wall. And look, this isn't a bug. It's a feature. The Layer 2 switch is doing its job perfectly. It's enforcing that strict isolation. The problem is, it just doesn't have the Layer 3 smarts to figure out how to route between those different VLANs. So we're kind of stuck, right? This isolation is fantastic for security and performance, but it's created these hard boundaries. To get across those boundaries, we need to do more than just switch frames based on a MAC address. We need to start routing packets based on their IP address. And for that, you're going to need a different piece of kit.
And this, my friends, is where the Layer 3 switch makes its grand entrance. This is how we get the best of both worlds, the solid segmentation of Layer 2 and the smart connectivity of Layer 3. The easiest way to think about a Layer 3 switch is as a hybrid. It's a super fast Layer 2 switch that's great at handling MAC addresses, but it also has a full-blown routing engine baked right in. That means it can make forwarding decisions using Layer 3 IP addresses. You get the raw speed of a switch with the intelligence of a router, all packed into one box. And this setup right here, this is the classic use case. It's called inter-VLAN routing, and it's what Layer 3 switches were born to do. The switch handles all the internal chatter between the VLANs at lightning-fast wire speed. This frees up your traditional router to do what it does best, handle that slower, more complex traffic going out to the internet. This design is just so much more efficient than choking all your internal traffic through a single router. So you're probably wondering, how on earth are these things so much faster than a traditional router?
What's the secret sauce? Well, the magic is in their internal architecture, and specifically how they separate the brains of the operation from the muscle. We call this the control plane and the data plane.
Let's break this down. First, you have the control plane. Think of this as the network's brain. It runs on a general-purpose CPU and does all the heavy thinking, like running routing protocols like OSPF to build a map of the network. Then you have the data plane. This is the muscle. Its job is simple. Take the map built by the brain and just forward packets. It's a simple but very, very repetitive job.
See, here's the problem with a traditional router. Its main CPU has to do both jobs. It has to do the thinking and the forwarding for every single packet. That creates a huge performance bottleneck. A Layer 3 switch gets around this by offloading that entire data plane, all the repetitive forwarding work, to specialized custom hardware called ASICs.
And this is the absolute game changer. An ASIC, an application-specific integrated circuit, is a chip that is custom-built to do one thing and one thing only: route packets at insane speeds. By taking this job off the main CPU and giving it to dedicated hardware, a Layer 3 switch can just blow a traditional router out of the water in terms of raw performance.
All right, we've gone through all the nitty-gritty tech details, from the danger of broadcast storms all the way to the power of ASICs. Now let's make this practical. Let's build a quick framework to help you decide when the Layer 2 switch is the right tool for the job and when you need to step up to Layer 3.
So when you're making the call, you really want to ask yourself a few key questions. First, is your network going to grow? Second, do you need to route traffic between different VLANs or subnets? If the answer there is yes, you need Layer 3, period. Third, what about performance? If you're running stuff like VoIP or video, you'll want Layer 3 features like quality of service. Fourth, security. Do you need to filter traffic with access control lists? That's a Layer 3 job. And finally, budget. Yeah, L2 switches are cheaper up front, but a single L3 switch might actually save you money compared to buying an L2 switch and a separate router.
So, to put it all in a nutshell, Layer 2 is all about MAC addresses and forwarding frames inside a single subnet. It's perfect for connecting users at the edge of a small network. Layer 3, on the other hand, adds IP address intelligence to route packets between different subnets. It is absolutely essential for the core of any large, complex network where you need things like dynamic routing protocols for scale and reliability.
And that really brings us to what's next. With technologies like software-defined networking, or SDN, gaining traction, those hard lines between Layer 2 and Layer 3 are starting to get a little fuzzy. We now have centralized controllers that can program the network's data plane directly, blending Layer 2 speed with Layer 3 smarts in really powerful new ways. So it leaves us with one final thought to chew on. In a future that's completely software-defined, will this fundamental distinction we just spent all this time on even matter anymore? Something to think about. Thanks for joining us.